Okay, so now we're given a steady state current through a wire on the x-axis, and remember, as discussed in the section, currents create magnetic fields, right? And the magnetic fields kind of wrap around the current. So this is a very convenient current in that it's just in a wire that's exactly along an axis. Now, the thing that's difficult about this, let's see here. So we want to compute the line integral of this magnetic field around a unit. Okay, and then there's some curve described. So all I have to do is draw the picture and apply the appropriate Maxwell's theorem, and then just see what the answer ends up being. So let me go ahead and just do this. So with picture, the current is in the x-axis. So let me draw this. Here's our current, and it's going in the direction of the x-axis. And let's see, the current there is equal to 6. Okay. All right. Now we want the line integral of the magnetic field around the unit circle in the YZ plane. Well, the unit circle in the YZ plane is, here's the YZ plane. I guess I got kind of lucky there. Let's see here. So there's the unit circle in the YZ plane, right? Okay. So what we're going to do here is we're going to go back and look and see where is the Maxwell's equation that directly relates to the situation where you have current and then you have a corresponding wire and you want to compute the line integral. So let's see, where is it? Here we go. Yeah. So here we go. Now, this comes out of this differential form of this Maxwell's equation, but the point is we have this calculation that shows that can be viewed in the integral form like this. And this says line integral of a magnetic field around the boundary of something is just mu naught times the current. So what we've got to do is look at our picture and ask ourselves how much current is going through this surface. And let's see here, let me draw the so there's our surface, and I want to know how much current is going through that surface. Well, quite a bit actually. I mean, this wire is going right through that surface. So there's your current. Does that make sense? Yeah. And so we know that the line integral around this boundary curve of b dot dx is mu naught I, which is then 6 mu naught, because I is 6. Does that make sense?
Yeah.
Okay. Now, let's see. I think I remember that there's a related problem right next to this. Let's see. This was this number? I've already forgotten. This was 7?
8.
This was 8. Right. Oh, yeah. No, this is a different. Okay, so I guess that's all. Is everybody happy with this problem?
Can I see the last one again?
Yeah. Yeah. So we're just using that. So this is Maxwell's theorem, the integral form of Maxwell's theorem. Yeah.
Isn't there a second part of the problem?
I'm sorry?
Isn't there a second part of the problem? Doesn't it?
Oh, that's what I was thinking of. Yeah, there is a second part of the problem. Excuse me. We just did the first part. Okay, second part of the problem. What's the line integral of the magnetic field around this other curve? So we have some new curve now, and it's parametrized by, well, let's see, x is always 3. That's interesting. And then y and z change. In fact, y and z do a little elliptical, they sort of elliptical little path around the point 3, 4, 3. So let's see here. This is going to be, let me draw a better picture here. So we're in the plane x equals 3. In that plane x equals 3, note that, does everybody see what I mean by we're doing an ellipse around the point 343? So here's the point 343. X is always 3. Y is sort of, it's plus or minus 1 from 4. And Z is sort of plus or minus 2 from 3. I claim that we're doing an ellipse kind of like that. That's our curve. Everybody see that curve? So that curve, of course, is in this plane x equals 3. And so the normal vector is going to be like that. Somebody have any question, or is everybody happy with this? Everybody good? Now, same deal, same current. We still have a current going through the x-axis. The current is still 6. Right? But in this case, the current is not going through the surface at all. It's going sort of around the curve as opposed to through the middle of the curve. So through that surface, there's no current. So when I try to apply this theorem, this current, the amount of current through the surface is 0. So I just get 0. You okay with that?
Yeah.
How about anybody else? Is everybody good? You look like you're just thinking about asking a question. No? You're okay?
Yeah.
Okay. Okay, yeah.
Could you do 10?
Yeah, let me wrap this one up first here.